right, continuing in chapter 23, looking more at the gas exchange and pressures that drive that. All right, so if we look first just at the behavior of gases, so again, that pulmonary ventilation, this is between the air and into the blood or out of the blood, that changes the volume of the thoracic cavity. So again, of course, the muscles used for inspiration increase that cavity, and that would include the diaphragm, the external intercostals, which are between our ribs, the pec minor, and the scalene muscles. All four of those are involved in allowing inspiration and increasing that volume. Then expiration, so exhaling, which decreases that volume, would be the internal intercostals, again, in between the ribs, the transverse thoracic, and some of the abdominal muscles help with that as well. So if we look at the muscles of that ventilation, we have two different things here. So we have quiet ventilation, and then we have labored pulmonary ventilation. So quiet is an active process. This is when the diaphragm contracts and it flattens downward. And then those external intercostals contract, and it raises the ribs and the sternum. That's a quiet inspiration. Now, forced inspiration, so we think about taking more like a really deep breath where we're forcing that, we have the involvement of the pec minor and the scalenes to contract. That's going to help raise the ribs and the sternums more to give a greater increase. So again, thinking about a really deep breath, then we're engaging the scalene and the pec minor. So that change in thoracic volume, so again, the diaphragm is going to contract, then the external intercostals are going to elevate the ribs. Then for the labored breathing, again, think about deep breath, then those additional muscles continue to expand the volume of that thoracic cavity. All right, now expiration is the same thing. Quiet expiration, this is more of a passive process. So now the diaphragm is relaxing and raises instead of being flattened out. Those external intercostals also relax to allow the ribs to come back down. So again, that's just a really passive process. Now, if we're forcing that, so again, having a deep like exhale or forcing all the air out, now we have the abdominal muscles contracting to push the diaphragm up more. And then those internal intercostals also contract to pull the ribs in to decrease that thoracic volume. So if it's just kind of a quiet expiration, it's just relaxing of the muscles. The only time we get contraction during expiration is whenever we're forcing that air out. So again, things here, that diaphragm and the externals are just going to relax to decrease the space there of that thoracic cavity. But then if we're forcing it out, then we're going to get the contraction of those intercostals. Now, the different pressure gradients are going to occur here. So we have what's called Boyle's law, and here we have P equals K over V. P stands for our gas pressure, V is for volume, and then K is a constant at a specific temperature. So thinking about normal body temperature. So what's going to happen here is the volume of the container increases. So this would be during inspiration. What's going to happen is the pressure inside decreases. So it's the opposite. So as volume increases, pressure decreases. As volume decreases, then that pressure is going to increase. So again, if we have Boyle's law here, so again, the pressure and the volume are inversely related. If one's going up, the other is going down. So just as pushing the plunger on the syringe, that decreases the volume. So now we don't have any volume in here, but now we've increased the pressure. Whereas once we've increased the volume of the space, there's less pressure that's being applied. So the gradient, the airflow, so the air always flows down the pressure gradient. So again, thinking from high to a low pressure. So during inspiration, the air is going to flow into the lungs, again, down the pressure gradient, because again, we're thinking about the volume is increasing, so the pressure is decreasing. So it's going to come into the lungs from high to low. Then during expiration, as the volume is decreasing inside that thoracic cavity, it's going to increase the pressure. So now it's going to leave the lungs going down that pressure gradient. So again, just as the blood flow, air flowing in the tubes because of that pressure gradient is going to occur. So we have a formula here, F equals the change in pressure, P1 minus P2, divided by R, and R is the resistance to that airflow. And then again, F stands for our airflow. So the airflow equals the change in pressure, so from pressure 1 to pressure 2, divided by the resistance. So the greater the difference, the faster the flow we're going to get. So there are different measurements of lung function. Most of these are using what's called spirometry, which is just measuring the volumes of air moving in and out by what's called a spirometer. So some of these volumes include tidal volume, or TV. This is the amount inspired or expired with each breath. So it rests at about 500 milliliters. You do not have to know the specific numbers, just kind of putting it into perspective. So just during a normal breath, that's referred to as tidal volume. Then we have an inspiratory reserve volume, and this is the amount that can be forcefully inspired. So again, if we're taking a deep breath in, normally it's about 500, but if again we involve contraction of those other muscles, now we can get up to about 3,000 milliliters. So a lot extra space is available, just not normally used. Then the expiratory reserve, again, now this would be what beyond the normal tidal volume that can be forcefully expired. So extra air that can be forced out of the lungs. Again, just putting it in perspective, about 1,100 milliliters. And then there's still going to be some air in. Even after you have a deep exhale, you forced all the air out that you possibly can, there's still air in our lungs, and that's referred to as the residual volume. So that's what's remaining after the forceful expiration, and it's about 1,200 milliliters. Now these different capacities then that we have, this would be the sum of 2 or more of these volumes that we just mentioned. So the inspiratory capacity, that's the tidal volume plus the inspiratory reserve. So again, the total amount that could be inspired, normal plus kind of that reserve. Then the functional residual capacity, or FRC, this is the expiratory reserve plus the residual volume. So again, after what's been forcefully exhaled plus what remains even after that. Then our vital capacity, this is the sum of the inspiratory reserve, the normal, which is our tidal volume, and the expiratory reserve. So kind of like the total amount of air that can be inhaled and exhaled is referred to as the vital capacity. And then total lung capacity is summing the inspiratory and expiratory reserves plus the tidal volume plus the residual. So again, total, everything added together. And this is just looking at some of those different volumes. So again, normal tidal volume, this is just what's kind of normally coming in and going out. If we force the air out, what additionally comes out is the expiratory reserve. Our maximum inspiration, so now we have our inspiratory reserve here that's coming up. If we add our tidal volume plus the inspiratory reserve, then that's our IC, our inspiratory capacity. Our vital capacity is the reserve plus the tidal volume plus the inspiratory reserve. Then our FRC, the functional residual, which is just kind of what's left after a normal exhale, which is the forced expiratory plus the residual volume that's left that doesn't actually leave. And then everything added together is our total lung capacity. Another one that we have here is what's called the forced vital capacity. And this is helping to look at lung performance to diagnose things like COPD, emphysema, bronchitis. So our forced expiratory volume 1, expiratory volume in a second, which is FEV1, 1 meaning 1 second. This is the amount of air expired within the first second of forced vital capacity. So the lower the volume, the more advanced the disease, indicating that, again, the emphysema or whatever has worsened. So the patient inspires maximally and then expires maximally as fast as possible. So how quickly can they do that in 1 second? That's looking at that forced expiratory volume. Some other rates that we can look at. So the respiratory rate, this is the number of breaths per minute. Minute volume is the total air that's moved in and out each minute. So that's the tidal volume times the respiratory rate. So again, the normal breath, the volume times how many breaths are taken in a minute. Alveolar ventilation, so the measure of volume of air available for gas exchange. So we have what's called the anatomic dead space, so that conducting zone space formed by the nasal cavity, the pharynx, all of those portions, that makes up that dead space. Then we have physiological dead space. This is going to be the anatomic dead space getting rid of, so, or plus, not getting rid of, sorry, that anatomic dead space, so in that conducting zone, plus the volume of any alveoli where the gas exchange is less than normal. And then we have the alveolar ventilation. This is the volume of air available for gas exchange per minute. So how much air can actually be exchanged during that minute. So what are some things that affect that ventilation? So we have increased vital capacity is correlated with being male. So there's more space, which means there's more air that can go in there. A taller height, activity. So again, exercise increases that vital capacity. Being thinner as well as just healthy, so not being in a disease state. So just to kind of put it in perspective, well-trained athletes can have a vital capacity about 30 to 40% higher than someone with a sedentary lifestyle. Now, in a healthy person, those anatomical and physiological dead spaces are about equal, meaning that most alveoli are being functional. So again, physiological is whenever there's alveoli, some of them aren't working very good, and that increases that dead space. They're not really involved in gas exchange. So people with diseases like emphysema, they're going to have large alveoli because those walls are degenerating, so they kind of like fuse together. But it gives less surface area for gas exchange, which increases more physiological dead space where there's not gas exchange occurring in those spaces. Now, compliance is another term, another measurement here. This is referring, though, to the ease that the lungs and the thorax expand. So how easily can you get a breath? And again, not a number you need to know, but 0.18 liters per millimeter mercury, which is a pressure term. Really what this means is the lower that value means that it is more difficult for the lungs to expand. So again, thinking about like emphysema where it's hard to get a breath, that number is going to be lower. Where we want to be is we want to have a higher value here, just meaning that the lungs are more compliant. It's easier for them to recoil and to be more elastic. It's easy to catch a breath. So that term is compliance. All right, now if we look at partial pressure, so this is the pressure exerted by each type of gas in a mixture. So now we have another law. So we had Boyle's law that was talking about pressure and volume. Now we have Dalton's law, and this says that the total pressure is the sum of all the individual pressures of each gas. So again, we're talking about like oxygen and carbon dioxide. We have other ones. So in this example down here, we have nitrogen gas, we have oxygen, and we have carbon dioxide. So if all three of these gases are in air, okay, then Dalton's law says that the total pressure we get by adding each of those together to get our total. So just adding them all together. Pretty easy. All right, so the sum of this, again, for atmospheric pressure, again, the gases we're talking about, of course, we mainly talk about oxygen and carbon dioxide, but there's also water vapor and there's nitrogen gas as well. All right, so if we look at these kind of at sea level, again, these are not numbers that you would need to know, but we also have different types of air. So we have like dry air, humidified air, but then if we look at alveolar air, you can kind of get an idea here of the different pressures that are happening. And we can also see, again, the majority of the gas pressure is from nitrogen, then oxygen, carbon dioxide, and then our water vapor. So yeah, the factors that cause differences in the composition include the air entering the lungs, whether or not it's humidified. So again, which is referring, again, dry air doesn't have water vapor, whereas humidified does have water vapor in it. So that can change it. The oxygen that diffuses from the alveoli into the blood, again, carbon dioxide goes from the blood to the alveoli. So again, talking about that exchange. And then it's only partially replaced by atmospheric air during each breath. So it's not a complete turnover. It's a mixing of those gases. All right, so the diffusion of gases, we have what's called the solubility coefficient. And this is the measure of how soluble a gas is in water. So does it dissolve in water? We have yet another law. Now it's Henry's turn. So Henry's law here says that the concentration of a gas in a liquid is determined by that partial pressure and its solubility coefficient. So how much of a gas we have in a liquid is based on that partial pressure and its solubility at a specific temperature. So we have concentration of dissolved gas equals the pressure of the gas times the solubility coefficient. That equals Henry's law. And that's what causes that hissing sound that we get whenever we open up a carbonated drink. So carbon dioxide is in here. It's dissolved in here. We don't see the little bubbles that are in here, but whenever we add oxygen to it, now we get the formation of that gas that's being released, and we get that dissolved oxygen leaving the solution as a gas that creates that hissing sound. Now we have a diffusion coefficient. I know, like you needed one more term, I know. So the diffusion coefficient, this is the rate at which the gas diffuses in and out of a liquid or a tissue. So again, how fast oxygen diffuses into the blood and carbon dioxide out of the blood. That's the diffusion coefficient. So our factors include the solubility coefficient, so how well it dissolves, as well as the size or the molecular weight of that gas. So just using oxygen here for an example. So the diffusion coefficient is actually 1. The relative diffusion coefficient for carbon dioxide is about 20. And so what this really means, what these numbers for these diffusion coefficients means, is that carbon dioxide diffuses about 20 times faster, more readily than what oxygen does. And a lot of that is because it's much more soluble in water than what oxygen is. All right, now we're going to switch over here a little bit, looking at these different pressures. So the physiology of ventilation. So we have the barometric air pressure. This is the air pressure outside the body. So thinking about the air. And then we have intra-air alveolar pressure, and that's the pressure in the alveoli. Okay, so what's happening during this quiet resting during our ventilation? So that alveolar pressure is equal to the atmospheric pressure. So again, we move from a high to low pressure. So if there is no difference, if there is no gradient, then there's no movement of the air. Now, when the alveolar pressure is less than the atmospheric pressure, again, we're going from high to low. So now this increases due to that volume. So again, back to Boyle's law, the volume increases, the pressure decreases. So now air moves into the lungs because the barometric pressure is higher than the intraalveolar. So it's coming into the alveoli. Now it then it reaches equilibrium and now becomes equal again to atmospheric at the end. So now air movement stops. Okay, then the opposite is going to happen. Now the alveolar pressure is going to be greater than the atmospheric because, again, that pressure change is due to the change in volume. So as our volume decreases, the pressure increases. Now the alveolar pressure is greater, and now air is going to move out of the lungs. So that movement of air is all based on that pressure gradient. Right? So again, just to put some numbers, again, not numbers you would need to know, but again, atmospheric barometric pressure is about 760 millimeters of mercury. And so again, whenever they're equal, so that's also what it is in the alveola. So whenever they're equal, there's no air movement. Now during inspiration, again, the barometric didn't change, but now we have a decrease in the pressure because our volume increased. So now that the volume here is increased, the pressure went down. So now air is going to go from the high pressure to low pressure. So air is going to come into the lungs. Okay, then now it's equal again. We're back to 760 and 760, so no air movement. Now what's going to happen though, as this volume in here decreases, now the pressure increases. So now it's higher inside the alveoli. So now that air is going to move out into a lower pressure gradient. All right, so what are some things that affect that ventilation? So the lung recoil, so again, kind of back to that compliance. So this is the tendency of the lungs to decrease after being stretched. So thinking about like a rubber band, so if it's really stretchy and it recoils back to its original shape and size, and it has good recoil. If you keep stretching it though, eventually it doesn't quite go back. It's stretched out and never goes back to its original size. So it's decreasing that recoil. So that elastic recoil is due to the elastic fibers in the walls returning to normal after being stretched. We also have our surface tension. So there's a film of fluid that lines that alveoli. Again, we have those type 2 pneumocytes that are releasing that surfactant. So we have some film, some water building up there. And those water molecules have a great attraction for each other. So that's going to pull them toward other water molecules, and that makes the alveoli collapse. So that surfactant prevents the tendency of the lungs to collapse. So again, it creates a fluid, a liquid there, again, produced with those type 2 pneumocytes to reduce the surface tension. So the water's not pulling on each other, it's kind of busted up by the surfactant. And then we have what's called infant respiratory distress syndrome. So this is common in preemies, so premature babies, because their lungs haven't completely developed, especially the type 2, so they don't have enough surfactant. So their lungs, those alveoli are going to collapse, and they're going to have much more dead space, and so they're not going to get enough oxygen to their tissues. Now we have a couple more pressures here. So pleural pressure, again, the pleural is that space. So this is the pressure in the pleural cavity, so between the parietal and visceral pleura. So a negative pressure here causes the lungs to expand during inspiration, and it pulls them back kind of like a suction. Then the alveoli expand when the pleural pressure is low enough, then they can overcome that recoil. And then we have what's called a pneumothorax in an opening between the pleural cavity and air. And this is going to cause a loss of that pleural pressure, which is helping the lungs expand. And it causes the lungs, instead of expanding, to collapse. So a pneumothorax is whenever we get a hole in that lining, messes up the pressure gradient, and the lungs collapse. All right, now if we look at a normal kind of breathing pattern here and what's happening with this pressure. So during kind of the normal quiet inspiration, again, that pleural pressure is going to decrease. Okay, then consequently, what's going to happen down here at 2 is that alveolar volume increases, then our alveolar pressure decreases below that, so air is going to flow into the lungs. So air is coming into the lungs now. Then what's going to happen is the air comes in, that pressure increases, becomes equal, and now we're going to stop the airflow. Okay, now that pleural pressure is now going to increase in step 4. So during expiration, that pressure increases due to the decrease in thoracic volume. Then our intraalveolar pressure increases. So now our volume, alveolar volume, decreases above atmospheric, and that air is going to flow out. Excuse me. The air is going to go out then of the lungs. And then the air flows out until that decrease, that intraalveolar pressure decreases back to the barometric pressure. All right, so some factors that can affect this. So the diffusion of the gas through the membrane. So again, that respiratory membrane, that's whenever we have the membrane of the alveoli up against the endothelial membrane of the capillaries. So there are 3 main factors that affect that diffusion. So the partial pressures, as we mentioned, again, the gases move from high to low pressure. So normally the partial pressure of oxygen is higher in the alveoli than the blood. So that's going to allow it to go into the blood. And then it's opposite for carbon dioxide. So it's lower in, the carbon dioxide is lower in the alveoli than in the blood. So it comes out. The membrane thickness. So the thicker that respiratory membrane is, the slower the diffusion is going to be. Again, just thinking about it has to move across those membranes. The farther it has to move, the slower it's going to go. And that's what happens with diseases like tuberculosis and pneumonia. It, due to inflammation, increases the fluid in between in that little space. So now it's a thicker membrane and the gas doesn't move as well. And then also the surface area. So decreased surface area decreases the diffusion rate. And again, that dead space is what we're talking about here, where those alveoli aren't actually doing anything. So things like emphysema and lung cancer, now we have more dead space, so less area for the gases to actually exchange. This is just showing that exchange here between that membrane. So again, here at the alveoli, the oxygen diffuses out. It's going to go into the blood, and then the carbon dioxide is going to go from the blood into the air, moving with those different partial pressures of each gas. All right, and this is just stepwising this out. I'm not going to read through each of these, but again, this is all, the movement here is all about the partial pressures and how they change. That's going to allow the oxygen to diffuse into the blood because it has a lower partial pressure. Oxygen or carbon dioxide, though, has a lower partial pressure in the alveoli, so it comes out of the blood into the alveoli. And then again, our carbon dioxide then is equal. So again, I'm not concerned that you know each of these numbers. I left these slides in here so that if it helps you to read through all of the steps in there, by all means, make sense of it the best way that you can. But it's all based on those movement from a high to low pressure gradient.